Hello again, higher algebra students, back here with the fifth and final lesson of our exponentials unit. This one is really just covering applications. So we really just want to look and see how does this exponential show up in the real world and what are the scenarios that it gets utilized in the real world. So when we think about the big picture here, we've talked about sketching exponential growth and exponential decay. An example of an exponential growth function, something like y equals 3 to the x, and decay would be y equals 1/3 to the x. And again, decay is where we're going down, and growth is where we're going up, not surprisingly. Now, an example of an exponential function that has two translations, again, that would be, say, 3 to the x minus 1 plus 5. Okay, so this would be your horizontal translation, and this would be your vertical translation here. And one that has a horizontal reflection, then it would be something like 1/3 to the negative x. Again, the horizontal reflection, which is over the y-axis, is the one that the negative is applied directly to the x. Again, a vertical reflection would have been a negative out front, like that. So, when we think about these real-world applications, one kind of example that gets thrown around a lot is this one here. Would you rather just be given $1 million or be given a penny that doubles every day for 30 days? And again, if you think about that problem and the exponential formula that goes with it, you think even after day 2, you would have, or excuse me, on day 2, you would get 2 to the first penny. So on day 1, you get 2 to the 0 penny, so you have 1 there. On day 2, you get 2 pennies. On day 3, so you can see the exponent is just 1 less than the day it is, 4 pennies. So if you go, say, 2 to the 29th, that's how many pennies you would get on just day 30. Again, because day 1, the exponent is 1 minus 1 to get you 0, so day 30 would be 30 minus 1 to get you 29. And 2 to the 29th alone means that you would be getting 5,000, excuse me, not 5,000. Let me just get all these values in here. This is how many pennies you're getting. So again, you divide that number by 100, which is how many dollars you're getting here. So you're getting about $5 million. 5, 3, 68, 709, 12 on just the 30th day of the month. So you can see it's how quickly it piles up, and again, that's the power of the exponential. So another area where this shows up is the idea of the rule of 72, which is how long it takes to double your money. And the years to double is 72 over the interest rate. So if your interest rate is 8%, it takes 9 years to double. If your interest rate is 6%, it takes 12 years to double, and so forth. So we just look at this formula and think about this with, say, whatever interest rate you think you're going to get, maybe it's only 3.4%. So you're going to divide this by 3.4%, or 3.4, again, the 72 here, since it's a whole number, we would just divide by 3.4 and not 0.034. So I just would take 72 divided by 3.4. Again, we kind of get rid of the percent there. So that means it'd take us about 21 years to double our money if we are getting a 3.4% interest rate. So, so this is one term, and you can see Investopedia is the source here. This is a big kind of common investment topic. So here's a real-world example with some actual values provided here. So if you think about, again, that the exponential is ab to the x, with a being our initial value. So in this case, McKenna's salary, initial salary in year 0 is $45,000. So A would then be 45,000. Okay. Now, an increase of 4% per year would mean really the 1, which is the rest of the salary staying stable, plus 0.04, which is the increase or the rate beyond just a stable salary that McKenna's going to get. And again, x is the number of years that we're talking. So year 0 is right now, but after 8 years, that would be an exponent of 8. So we'd have 45,000 times 1.04 to the 8. And again, the 1.04 to the 8 alone gives us about 36.9% in terms of an increase over that period of time, but we take 45,000, multiply it by 1.04 to the 8, and that would give us an ending salary of about $61,585 and 61 cents. So this would be the salary after 8 years, provided we get that 4% bump each year. And again, we could take this further and change the number of years from 8 to 18 or do whatever else we wanted. There's some other additional pieces that we could do as an enrichment activity here in terms of maybe the increase isn't annually, maybe it's biannually or things like that, but we'll just keep it right here. So that example covered a version of the compound interest formula where really in that case the increase or the interest was applied only once during the year. So it was when we look at annual rate of return, it literally was that 0.04. Compound interest oftentimes has a certain denominator here that represents the number of times that interest is applied per the time period, and it gets brought up here as well. And we're going to kind of avoid that for now and just really leave it at n equals 1, which would be just once per year that this change is occurring. But really what actually happens, for instance, in investments, is it's changing daily in terms of that interest. The 4% would be applied to a different dollar amount really every day or every minute, depending on how frequent these change. So in general, the final amount is going to be the beginning amount, the principal, which was McKenna's first year salary there. The 1 again just brings in the idea that we're keeping the value that we had and either adding or subtracting from that. And then R would be that rate. And again, the N we're not going to get too caught up in right now, and T would be the number of years there. So here's an example again. If we have an inflation rate of about 2% per year and a gallon of milk costs $3.49 at Target, how much will it cost in 2025? So again, the Y, or whatever the value is, it has a $3.49 starting point. The 1 means that we're just keeping that value stable, but we're adding in 2% per year, and this would be for the next 4 years as of 2021. And so again, we've got 349 times 1.02 raised to the 4th, and that would mean that in 4 years, we could expect a gallon of milk at this inflation rate to cost about $3.78. So it would go up almost 30 cents over the next 4 years at an increase of 2%. And of course, aside from inflation, there's a lot of other things that can influence the price of milk in terms of supply and demand. But if you're looking at just this inflation. So this idea of growth also applies naturally to decay. So if you think about cars is depreciating in cars is one of the more common things. And new cars depreciate faster because if you think about the kind of general pattern of depreciation, new cars are over on the left part of this decay. Older cars are on the right part of this decay. And again, this is typically kind of the pattern. So those first couple of years, in particular, you can see here after 1 minute and then 1 year and 5 years, what happens to these cars over time. And again, this is same sort of exponential formula. It's just that instead of adding an R, we're really kind of subtracting an R. And so if it loses 20% of the value, it's 1 minus 0.2 rather than adding 20%, which would be 1 plus 0.2. So as an example here, we have a car that's purchased that's $25,000. So that's our initial value here. And again, it depreciates 17% per year. So again, that 1 still comes along for the ride, but now we're subtracting 0.17, and we want to see its value after 7 years. So what we're doing here then is we're maintaining 83% of the value each year. So if we take that 83% and raise it to the 7th and multiply that by the initial value of the car after 7 years is worth $6,784.01. Can't forget that 1 cent, very valuable here. And so what's happening is we're actually about 27% of the original value when we took this 0.83 to the 7th. That gave us kind of the total percent of original value that we were going to have, knowing that each year is going to be 83% of the previous year that we had that car. And again, it's really happening gradually, day by day. It's not, as of July 1st every year it drops 17%, of course, but in general, this is what's happening with cars, is they're depreciating. Over the span of a year, they're depreciating by about 17% on average. So here again, just to conclude, here's the actual compound interest formula. And again, a lot of the same things, the future value, the principal are the same as we've been looking at. This one up front is the same as we've been looking at. The T still tends to be something like a year, most commonly. The R, the rate, is what we're used to seeing now, but these N's that I was referring to a couple of slides ago, this would factor in like if it's occurring monthly in terms of these rates, or if it's daily or weekly or whatever it happens to be. Monthly or every 6 months, biannually, tend to be, or daily tend to be what we see most often perhaps, but we aren't going to jump into any problems specifically with this, but this would be kind of that next level activity here as we look at exponential growth and decay. We'll leave it at that. Thank you everybody for watching and listening, and if you have any questions, as always, please ask.